For quiz 6, we're going to go over how to evaluate a limit. The first 6 problems on your review look like this. Let's take a look at the functions that we have here. Here we have a radical or root function. Then we have a polynomial, quadratic. Here is another polynomial, constant, which is a type of polynomial. Another radical or root function, and rational function. For every single one of these, as long as it does not make the expression undefined, you can use direct substitution. In this case, direct substitution, 3 minus 3. How does that actually look? I'll show you that. This expression is undefined, so immediate direct substitution does not work. Sometimes we just need to do some algebra to manipulate the expression first before we can evaluate the limit by direct substitution. In this case, we're going to factor, and hopefully that will help us reduce. All right, we have a special form of the number 1. Now we're trying to find the limit as x approaches 3 of x plus 4. Direct substitution in this case would not yield an undefined expression, so plug in the 3 and you have your limit. To combine the many fractions, we need to get the LCD. The denominator here is x plus 5. The denominator here is 5. The LCD must be 5 times x plus 5. So we're going to multiply each of these fractions by what they're missing that's in the LCD. This denominator only has a 5 in it. We're going to multiply it by x plus 5 over x plus 5 because that's what's missing in this denominator that's in our LCD. This one we're going to multiply by 5 over 5 to get a common denominator. We have 5 over 5 times x plus 5 minus 1 times x plus 5. So make sure that you remember to distribute that negative over 5 times x plus 5. Now they have the same denominator, so let's combine those fractions. Distribute the negative. 5 minus x minus 5 over our denominator 5 times x plus 5. Okay, these 5s will reduce to 0. I will write the numerator as a fraction just to keep track of my numerators and denominators. Over negative x over 5 times x plus 5. You now have a fraction divided by a fraction, so we can change it to multiplication and flip it. We'll reduce these fractions and end up with no longer a rational expression. You have x over x is 1. This negative, bring it up, make sure you don't forget about it. So negative 5 times x plus 5. At this point we can use direct substitution. Negative 5 times negative 5 plus 5 is negative 5 times 0, which is 0. And that's our limit. A rational expression with a radical, and then you can't use direct substitution? Oh no. So in this case, we're going to rationalize the denominator, see if that helps us. In other cases, we rationalize the numerator. just can we rearrange it in any way to be able to direct substitute? Okay, that's the goal. So to rationalize this denominator, I'm going to multiply by the conjugate, which is square root x plus 6 plus 3 over square root x plus 6 plus 3. I'm leaving the numerator factored just to see if something may reduce. Okay, a radical times a radical gives me just what was under the radical, x plus 6. Because these are conjugates, your middle term will cancel to 0, so you only need to multiply the first and last terms. Negative 3 times positive 3, that one is negative 9. Let's go ahead and simplify the denominator. Hey, that reduces to 1. X plus 3 over x plus 3 is... We're left with the limit as x approaches 3 of square root x plus 6 plus 3, and now we can direct substitute. And that would be 6. Here we have the beautiful floor function. What a strange thing. Plug in some values around 3 to see how it looks. Now we really care about approaching 3 from the right, so from the greater than. So just to get a little sense of where we're at, I'll start with 2.5. Then we'll plug in 3, 3.5, 4, and 4.5. Negative 2.5 plus 1, that is negative 1.5. Okay, what does the floor function mean? It means the integer, you return to the integer that is less than or equal to the number inside here. So what integer is less than or equal to negative 1.5? That is negative 2. Continue plugging in. The integer less than or equal to negative 2 is negative 2. The greatest integer less than or equal to negative 2.5 is negative 3. For negative 3, it's simply negative 3. And less than or equal to negative 3.5 is negative 4. Let's go ahead and graph this floor function. I think the trickiest part about graphing a floor function is kind of knowing where your holes are. When we plugged in 2.5, we got negative 2. When we plugged in 3, we get negative 2. At 3.5, we get negative 3. At 4, we get negative 3. At 4.5, we get negative 4. So what's happening is that there's clearly a point at 3, negative 2. There's clearly a point at 4, negative 3. So this one's headed this way. This step has to go all the way up to right underneath this one. So if 3, negative 2 is a point, then 3, negative 3 has to be a hole. Otherwise, it's not a function. Okay, that extended for the width of 1 unit from 3 to 4. So these will all extend for the width of 1 unit. 3 to 2. So at 2, negative 2 is where I'll put my next hole and continue building it. Going up, 1 unit, and then a hole. Here we should have a hole directly underneath that, and then going 1 unit to the right. Here is our floor function. So now what is the limit as x approaches 3 from the right-hand side? As we're approaching 3 from the right, we are approaching -3. And that's our limit. To find the limit of an absolute value function, we need to know this very important property. Absolute value functions are just two lines that meet at a point, and so we can always write an absolute value function as a piecewise, and this will help you find your limit. Now, if there is some sort of horizontal shift with your absolute value, such as you have absolute value x minus h over x minus h, and similarly x minus h over absolute value x minus h, this would end up giving you the same piecewise values, except your transition point x value would not be 0, it would be h, whatever the shift that has happened is. For this example, we will first simplify and then use these properties. Let's factor out a -2 from the numerator. And also, I don't like this negative in front of my x. I want it to just be x. So I'm going to factor out a -1 from the denominator. It's all still in the absolute value for now. I must also remind you that absolute value A times absolute value B is absolute value AB. So we'll write the denominator as the product of two absolute values. So absolute value -1 times absolute value x minus 4. Evaluate the absolute value of -1. That's just going to be 1. We're almost there. It almost looks like the form that we're going toward. Let's take out the -2. So -2 is being multiplied by this fraction. I'll write it as -2 times the limit of, as x approaches 4 from the left, of x minus 4 over absolute value x minus 4. That's -2 times this limit. What is this limit? H is whatever makes this equal to 0. X minus 4 equals 0, h is 4. So the piecewise function that this absolute value gives us is that it's going to be approaching -1 when x is less than 4, but it's going to be approaching 1 when x is greater than 4. This is approaching 4 from the left, that's -1. -2 times -1, our limit is 2. When approaching limits at infinity, we can also use direct substitution for rationals, radicals, polynomials, except we cannot get the result of an indeterminate form. Often the goal is to get the variable to be a denominator because we can plug infinity into a denominator much more easily and get an actual result. The first thing I see with this example is that there is a square root over the entire function. I'm going to immediately take that out of the limit. So say we're going to take the square root of the limit of this rational function as x approaches -infinity. Oftentimes with limits at infinity, we actually take a rational function and we try to make it into complex fractions, okay, into a more complicated fraction. So we're going to multiply this by a special form of the number 1 in order to make the variable be a denominator. I'm going to choose 1 over x squared because 2 is the highest degree of either the numerator or the denominator. 1 over x squared times x squared is 1. 1 times 1 over x squared is 1 over x squared. This gives me 4 plus 5 over x squared. Now I can use direct substitution for negative infinity. 1 divided by infinity is 0. 5 divided by infinity is 0. The square root of 1/4 is 1/2. Find the intervals on which each function is continuous. Let's look first at what type of function we're dealing with so that we know characteristics of its continuity. For example, number 20 is a polynomial. That one's easy. All polynomials are continuous from negative infinity to infinity. Done with number 20. Okay, piecewise functions can have continuity or discontinuity. So you could have the two pieces could meet, or the two pieces could not meet, and there could be some sort of jump discontinuity. To check if the pieces meet, plug in the transition point x value. So I need to plug in 2 to the first piece, and then plug it into the second piece. Now I know it's not in the domain of the second piece. I don't care. I just want to know where that point would end up if 2 was plugged in. Negative 4 plus 4 is 0 minus 1, and then 4 minus 2. Okay, these numbers do not match up, therefore this function has jump discontinuity at x equals 2. So the intervals of continuity for this function is everything leading up to 2. And the first piece was the piece that included 2. So make sure you look out for these inequality symbols will help you with your intervals. This includes the 2. And then this one has a parenthesis, okay, parentheses from 2 all the way onward to positive infinity. For rational functions, there are 2 things we need to know. Number 1, wholes are removable for rational functions, and 2, vertical asymptotes are never removable. To find the wholes, we're going to factor. Anything that reduces to 1 is a whole. X minus 2 over x minus 2, that reduces to 1. So we have a whole at whatever makes this 0. So what minus 2 equals 0? That would be 2. So we have a whole at x equals 2. The function that we're left with after the reducing is negative 1 over x plus 2. There's still a restriction. There's still something that can never ever be plugged into this, and that would be negative 2. So what you have here is a vertical asymptote at negative 2. So these are 2 points of discontinuity. This one is removable, and vertical asymptotes are never removable. The intervals for continuity start going from negative infinity up to negative 2, then from negative 2 to 2, and then from 2 to infinity. If you're confused on parentheses or brackets, it's always parentheses unless it includes the actual number. Wholes, asymptotes, those do not include the actual number. Okay, so the only time it included it was for this piecewise function when it actually told us that in the inequality symbol. So my intervals for continuity are here. You can put commas or you can put U's in between.